Hey guys, it's Jessie. I'm going to be working through the answers for week 1's recitation packet for Dr. Collini's CHEM 2380 class. Question 1 asks, what 4 features of a molecule can you learn from NMR? So those 4 features are, number 1, the number of unique proton environments. So what I mean by this is the number of signals that show up on the NMR graph. So if there's 2 signals, that is equivalent to 2 unique proton environments. The second thing is the number of protons within each environment, and that is found by taking the integral and finding the area under the curve for each of the peaks. And then the area is going to correspond with the number of protons that are contained within that proton environment. The third thing that you can find is how many neighbors the proton has, and this is found by looking at the splitting pattern. So again, if the number of neighbors equals n, the splitting pattern is going to be n plus 1. Finally, the last thing that we can learn from an NMR graph is the electronic environment around the protons. So this means like how much electron density is around them, and this is determined by the shift or how far upfield or downfield the signal presents itself. Question 2 asks us, what does downfield versus upfield mean, and what does deshielded versus shielded mean? So I'm drawing kind of just a rough sketch of an NMR graph. Over to the left side, this is going to be downfield, so the larger numbers, more towards the left, this is downfield. It corresponds with being deshielded or less electron density. And then over to the right with the lower numbers, this is considered upfield. This is where you find protons that are more shielded, or in other words, they have more electron density. And again, I'm just going to write that off to the side as well. Deshielded means less electron density, shielded means more electron density. The next question asks, how do you determine splitting? So like I'd said in question 1, splitting is equal to n plus 1, where n is referring to the number of proton neighbors, or in other words, the number of protons that are on adjacent carbons to the protons of interest. So as an example, I'm going to draw ethyl chloride, which is going to have these 2 protons in green, and then the 3 protons in yellow. Those are each in their own unique proton environment, so there's going to be 2 signals that show up. The protons in yellow have 2 neighbors, or in other words, 2 protons on the neighboring carbon. So that means that n equals 2, so the splitting is going to be 3, or a triplet. And then for the green protons, n is equal to 3 because they have 3 proton neighbors, or in other words, 3 protons on the adjacent carbon. So if n equals 3, the splitting is going to be equal to 4, so it's a quartet. Question 3 asks, how do you know the number of hydrogens in a given peak? And again, like I had said in question 1, this is found by integrating to find the area under the curve. And then if you need to scale the numbers to the whole number integer, those whole number integers will be the ratio of protons contained within each of the peaks. So using the same example from above, we have that ethyl chloride again. I'm just redrawing these peaks down here. The first one, let's say this is going to integrate to a value of 3 because there are 3 yellow protons that are making up this signal, and then similarly the green peak is going to integrate to an area of 2 because there are 2 protons within that one. Question 3 asks us to give an overview of where we expect to find the proton associated with each functional group. So the first one is an alkyl group. This can be primary, secondary, or tertiary. So I've drawn here RCH3, or also like R3CH or R2CH2. These are all going to be relatively nonpolar bonds. There's about equal sharing between the carbon and the hydrogen. So these are not going to be very deshielded at all. So we're going to find them between about 0.9 to 1.7 parts per million. Up next, we have an aldehyde. This hydrogen is going to be much more deshielded because of the carbonyl group right next to it. So it's going to be found far to the left of the graph, up near about 10 parts per million. Number 3 is an ester, and I think this might have been either a mistake or something that you guys don't necessarily need to know because this isn't found in the table that's given to you, that's provided to you. So I'm assuming that we're talking about the hydrogens that are attached to the carbon attached to the oxygen. I know that's kind of confusing. You're not given a value for this in the table, but these hydrogens are attached to a carbon, so we can imagine that they're probably going to be pretty similar to the alkyl group, maybe a little bit more deshielded because the carbon is attached to those oxygens. So I would guess it's going to be around 1 to 2 parts per million. Up next, we have a benzene ring, and despite being a carbon-hydrogen bond, the resonance that takes place within the ring ends up making the protons on the outside surprisingly deshielded, so these are going to be found between 6.5 to 8 parts per million. And finally, we have alcohol, which is a proton attached to an oxygen, so this is a relatively polar bond, so the proton is going to be deshielded, and these are going to show up between about 2 to 5 parts per million. Question 4 asks us how many signals we would expect to find in the proton NMR spectrum for the following molecule. So the first thing that I would do is draw in all of my implied protons so I can see where they all are at. And then the next thing that I do is I notice that there is a plane of symmetry right down the middle of this molecule, and because of that, the 2 protons on either end, even though they are bound to 2 separate carbons, they're actually going to create one signal because they are in identical proton environments. So this molecule is only going to have 2 signals. So just to reiterate my process, the first thing that I did was I drew in all of my implied hydrogens, and then the next thing I did was I looked for symmetry to see if there might be 2 different protons contributing to one singular signal. Question 5 asks us what we would expect the integration and splitting pattern to be for that molecule. So I'm going to use yellow to denote the signal coming from the 2 highlighted in yellow, and then green for the signal coming from the highlighted protons in green. And again, we're looking for integration. I'm going to find N and then the splitting. So the protons in yellow should integrate to 2 because there are 2 protons making that signal, and then same thing with the ones in green. There are 2 protons making that signal, so they both integrate to 2. To find N, we are looking for the number of protons that are on carbons adjacent to the protons making our signal. So for the yellow protons, they are each adjacent to the carbon containing the green protons, so they each have 2 neighbors because they're both adjacent to the green carbons in the middle. And then similarly, if we're looking at the protons that are making the green signal, they are each adjacent to the yellow protons, so again, they both have 2 neighbors as well. So from there, to find splitting is always going to be equal to n plus 1. So if n equals 2, our split is going to be 3 for both of these, so they're both going to be triplets. Question 6 asks us to identify the chemical shift, the integration, and the coupling for the hydrogens that are indicated by the arrow. So I'm going to write those all down, and we're going to go one by one. So up first, we have these protons that are attached to a carbon, which is then attached to an oxygen. We know that the carbon-hydrogen bond is going to have a shift around 1 to 2. That oxygen might bump it up a little bit, but I'm still just going to write that it's about 1 to 2. And then integration is found by looking at the number of protons that are contained within the signal. So in this case, there are 3 protons that are making up the signal, so the integration is 3. Splitting refers to the number of neighbors, but because these protons are attached to a heteroatom, that is going to disrupt the whole neighboring system. So these are going to have 0 neighbors, n equals 0, therefore the splitting is 1, so it's going to be a singlet. Up next, we have this primary carbon that has 3 protons on the very end. So I'm going to draw those 3 in so you can see what we're talking about. Because this is a carbon-hydrogen bond, this shift is also going to be around 1. Again, it's primary, so closer to 1 rather than 2. And there's 3 protons here making the signal, so the integration is 3. Then for splitting, there's only 1 neighbor on that adjacent carbon, highlighted in blue there. So the splitting is going to be 2 or a doublet. Up next, we have the protons that are on this secondary carbon that is adjacent to a nitrogen. So again, this is a carbon-hydrogen bond, so probably around 1 to 2, but maybe slightly higher because of that neighboring nitrogen. The integration for this is going to be 2 because there are 2 protons that are making up this signal. To find N, we are going to look at the protons that are on neighboring atoms. So on the left, we have 2 protons that I've drawn in blue, and on the right, we have this nitrogen, so there's no neighbors off to the right. So N is going to be equal to 2 for those 2 neighbors. And then if N is equal to 2, the split is going to be 3, or in other words, a triplet. And finally, we have this secondary carbon that's going to have 2 protons coming off of it, and it's attached to an ether on the right side and a benzene on the left. So I'm drawing in these protons, but as you can see, they're both going to be a little bit more deshielded than, for example, like question 1 up at the top, because of the 2 electron withdrawing groups on either side of it. So I'm writing down that it's 1 to 2, but it's probably closer to 2, if not maybe a little bit higher. These protons are not going to have any neighbors because to the right we have a heteroatom and to the left there are no hydrogens on that adjacent carbon. So n is equal to 0, which gives a singlet, and the integration is 2 because there's 2 protons that are making the signal. The last question asks us to indicate the shift, the integration, and the splitting pattern for the protons that are on the benzene ring of the molecule above. So I'm going to start by just drawing in all of the protons that we're talking about. There's 5 of them, so the integration should come to 5. And because they're all technically in their own environment, we're going to get a multiplet out of this. We're not going to see really any distinct splitting. And the shift is going to be about 6.5 to 8, again, because these protons are all attached to a benzene ring. Now shifting over to IR, we're asked to identify 3 features that we should pay attention to. The first one is wave number. This tells us the type of bond that we are going to be, that's going to be represented by the signal. Number 2 is the intensity, and this tells us the polarity of the bond. So the more intense the signal, the more polar the bond, because increase in polarity is correlated with an increase in percent transmittance, which is what the signal on the graph is showing us. And number 3 is the shape of the peak. So is it really broad or is it really narrow? This is going to indicate hydrogen bonding. So the more broad and spread out the peak is, that's going to indicate that hydrogen bonding is present in the molecules. The final question asks us, what is the fingerprint region and is it useful for identification? So the fingerprint region is about from 400 to 1500 wave numbers, and it's not super useful for identifying specific bonds or molecules because there's too much variation to visually recognize any useful patterns within this region of the graph. So that wraps up this review video for week 1's recitation packet. I hope it was helpful. This is my first time making a video, so if you have any suggestions on improving the format or the structure of the way that I go through these videos, please feel free to send me an email. I'm going to be kind of experimenting with a couple of different styles for the first few videos that I make, just trying to figure out how things work best. So if you have suggestions, please let me know. And again, if there's any questions you have about specific questions or answers that I gave in this video, again, feel free to reach out, send me an email, we can talk, we can meet during my office hours. I'm happy to go over things in more detail if there was anything that was still left unclear.